All right, everybody, welcome back. So today we're just going to go over the last little part of the exercise session that we did not get to, and that's going to be on Lecture 8, which is enzyme kinetics. Now, I know this was a lot of math thrown at you, but the good news is that on the exam, you could expect to have a max of maybe 3 questions out of 50. On my exam, when I took it, there was only 2, and then one of them was pretty easy. And then the other question was kind of tough, but it was still doable. However, we're just going to jump right into some practice problems because I think that's really the best way that you can start to get the feel for things. And when you start aligning words with graphs, then it really does help you figure out exactly what's going on with all the scenarios. So basically, enzyme kinetics, it's really helpful because there's going to be a lot of inhibitors, there's going to be a lot of promoters, there's going to be a lot of things that can shift the equilibrium of any reaction to either side, and we're going to see that a lot of times throughout this course. So having the kind of math knowledge in the back of your head of how it happens is going to be really important to understand a lot of things in the course. So basically, let's just go on with number 1, which is to label the double reciprocal plot with the letters corresponding to items A through G. As you can see, I already have it all marked up, but we're going to go through explaining exactly why everything is labeled the way it is. Now, just one thing to know about the double reciprocal plot is that it takes all those curves that we dealt with, and because sometimes curves can behave weird, and the reason for curves and asymptotes, can mean fuzzy things in not necessarily fuzzy, but they mean something in biochemistry. But when we do the double reciprocal plot, we get rid of curves and we turn it all into linear relationships, and we're going to see what some of these mean. Okay, so let's just start by talking about our axes real quick. It's 1 over substrate concentration on the x-axis, and it's 1 over velocity on the y-axis. So that's items D and E below. So whenever we're dealing with inverse, you kind of have to think a little bit backwards sometimes. If we increase the substrate concentration on this graph, or let me get my thing back up. If we increase the substrate concentration on this graph, so I'm going to align my thing with red so we know what we're talking about. Increasing the substrate concentration is actually moving to the left, because if you make the denominator smaller, it's going to be a bigger number. So going that way to the left is your bigger substrate concentrations are going to happen over here. And if you increase the number that we're plugging into 1 over S, it's going to get smaller, so that's going to be way out here. So stuff happening with little substrate concentration is going to be out in this region of the graph, all the way out here. And things with higher substrate concentration on the double reciprocal graph are going to be happening over here, closer to the origin. Same story with 1 over velocity. Your occurrences of higher velocity are going to occur down here, close to the origin, because once again, it's a reciprocal. I'll switch to blue so we know what we're talking about. So 1 over velocity, your higher velocities are going to be happening down here, and your lower velocities are going to be happening all the way up here, far away from the origin. So now that we have that established, let's get into our lines and what they mean. So the yellow line is labeled as no inhibition. It's basically, and I'll switch to yellow. It is basically saying that there's an enzyme and a substrate, and there's nothing messing around with it. There's no drugs that you put in that inhibit these enzymes. There's no toxins that are going to mess up the enzyme as well. There's no bacteria inside your body eating your substrate that's trying to react with the enzyme. You can make up a lot of interesting scenarios as to what it would be. It's probably not too important, but it's just an unaltered enzyme. So now we have and I will switch to green right here. What we have in green is our non-competitive inhibition. So what non-competitive inhibition is, it's when you have, and I'll try to draw something out. If you have like an enzyme, this is going to be really ugly. But But if you have an enzyme right there and it has an active site, you know, your substrate, which we said was, I'll change that to red, because substrate was red. So non-competitive inhibition, your substrate is going to want to bind to that active site right there. However, what a non-competitive inhibitor does is, all right, I should have made the green a different color. All right, so from now on, we're going to make this, what color do we want? All right, so the dark green, and now in this example, is going to be the non-competitive inhibitor. What the non-competitive inhibitor is going to do is it's going to be really sneaky, and it's just going to bind somewhere different on the enzyme, like right over here. And what that's going to do is that's going to completely invalidate the normal active site. It's going to maybe make a conformational change in the enzyme, or it's going to close it up or something like that. And whenever you do that, this whole entire thing is just void of any, and the layering is a little bit off there, but a non-competitive inhibitor is going to bind somewhere else on the back side of the enzyme, you name it, wherever, and it's going to make the active site unable to bind the red substrate up there. So that's what a non-competitive inhibitor does, and it has this line, and we'll talk about the shape of the line soon. And now the last thing we want to talk about is the competitive inhibition. And what that is basically, and so I'll just redo a color scheme. Imagine you have this enzyme, and it has an active site. We'll make it purple this time. That doesn't correspond to the purple over here. We're just making a totally different scenario. So what a competitive inhibitor does is, you know, we have our red substrate that is supposed to react. There could be a lot of them out here, you know, whatever. All these are wanting to react with the purple active site. However, what a competitive inhibitor does, and we will make this color, let's see, we'll make this pink. Okay, so what a competitive inhibitor does is that it mimics the substrate. So you're going to have a whole bunch of competitive inhibitors out here, and now there's a 50-50 chance, if they're in equal amounts, that instead of red binding to this active site, so I'll just draw it over here, what I just made right there. So instead of the red binding to the active site, just like we want it to, what's going to happen is that a pink is going to bind, which is our competitive inhibitor, and it's just going to bind to the active site. So basically, it's not going to bind somewhere on the backside, like down here, and just close off and make the active site unable to bind. Competitive inhibitors are literally just going to compete for the same active site that our normal substrate in red is going to react, or is going to try to go after. So I know I kind of just made up that shape and everything, but I hope that makes sense. So now we have to think about what are the lines telling us. So now we're back over to here. And before we talk about exactly the lines, we have to talk about these little dots that we made over here. So we're talking about purple. So 1 over V max are these two purple dots right here. So the y-intercept of the double reciprocal plot is going to be our V max, because that's when the substrate concentration is highest on the reciprocal plot and the velocity is the highest. So these linear plots are going to intercept right here at the maximal enzyme velocity. And remember, the enzyme velocity is the maximum rate of function of the enzyme. So if we think about this, if we have no inhibition, then it's going to have a Vmax. So everything in the yellow in all of its properties are just reference. So now if we go back to our competitive inhibitor, which is right here, if we go back to our competitive inhibitor, that's like this situation out here. They're going to be binding for the active site. So if we take a look at our Vmax for the competitive inhibition and no inhibition, they are actually going to be the same right here at this bottom purple dot. And why is that so? So this is going to be the same thing because theoretically, like, even though in our example over here, the competitive inhibitor in pink, it is present, the enzyme is not being altered in any way. It just has different things binding to it. So theoretically, even though there's annoyances around, the maximum velocity that this enzyme could achieve is the same for competitive inhibition and no inhibition, because it's still only dependent on the red dots over here are normal substrate binding to that purple active site that we have right there. So that's why competitive inhibition and no inhibition are going to have the same Vmax. So now that we have that out of the way, you have to, let's just do a quick thought exercise. How can we actually prove that this would be the case? Well, it actually gets kind of easy. So I'm going to erase some of these guys that we have over here, and hopefully not erase other parts of my diagram. Okay, so imagine I'm just going to override that pink. No, it doesn't want to override. I can fix that. Okay. All right. So imagine, once again, we have our active site right there. And although, let's just say that there was, those annoying little other inhibitors, the competitive inhibitors that are going for that same active site, what would just happen if we put a whole bunch more of our normal substrate out here to the point where that there's hardly any competitive inhibitor? If we do that, then we can really say that, okay, well, the competitive inhibitor being present isn't going to affect anything. So that's why you can theoretically say that even though a competitive inhibitor is present, the Vmax for the reaction is going to be the same, because you can just drown out that competitive inhibitor and it's going to be like it's not even there anyway. So now that leaves our other model, which is the non-competitive inhibition. And I'll switch back over to this color so I know what we're talking about. So now we're talking about the non-competitive inhibition. And we notice that this does not share the same Vmax. Notice we have the purple intercept right here, and then the top purple intercept. So Vmax on this graph has it's traveled up on the y-axis for the non-competitive inhibition. And remember, we're talking about reciprocals. So this is higher on the y-axis, which means it's a lower velocity. So in non-competitive inhibition, our Vmax has lowered. And why is this the case? This is the case, and it goes back to our drawing up here, and I know these aren't super pretty, but I hope they get the point across. In our drawing up here, this dark green is representative of the competitive inhibitor. So it binds to some other site on the enzyme. It does not bind to the active site. It's not like the competitive over here that they'll both bind to the active site. This binds somewhere totally different from the active site. So why we say that the Vmax technically drops, in this case it's showing a small drop. It could, depending on how much non-competitive inhibitor, it can be a really big drop. However, why we're saying it drops is because, let's take some more look at our dots. If this is our non-competitive inhibitor that is successfully binded over here, and what it's going to do, it's going to inactivate that active site, which is why I have an X through the black dot, which is our active site in this case. So if you think about it, let's just say we have a whole bunch of red substrate out here. It's perfectly good substrate. There's nothing going on with that. But no matter how much of it there is up here, it's not going to be able to bind to our active site at all, because our non-competitive inhibitor has its own special way of screwing up this enzyme. So it basically takes the enzyme and it makes it completely useless. And that is really, messing with the enzyme is really the only way you can affect the velocity, because we're talking about enzyme kinetics. Substrates don't have kinetics, they just have concentration. But the enzymes, they have kinetics, which means it kind of relies on everything. And because this enzyme is totally useless, then the overall, like if you have enzyme in a beaker and then you're pouring substrate into it, if you have competitive inhibitor in there, there's nothing that can be done. And the velocity in your beaker that your beaker is capable of with all the enzymes and the substrate in there, it's going to just drop because there's nothing that can be done about it. So that's what this purple dot right there is saying, and that's why the non-competitive inhibitor has a lower Vmax, which is higher on the reciprocal plot. And now basically the last thing that we need to talk about, and these three lines and the velocity intercepts are the most important. The last thing we need to talk about is the Km values. Now I know most of the double reciprocal plots he gave you, he didn't even include the negative quadrant over here, so I doubt he's going to answer a question on this. But basically what it's saying is that the Vmax is on the x-intercept, and it's really not worth explaining too much. However, we can see that there's certain values that are shared right now, and actually we're not going to get into this because this is a little bit you're not going to get tested on this, I would believe, talking about the negative quadrant on a double reciprocal plot. On question number 3, we will look into that a little bit more. But and it gets tricky over here because you're doing a reciprocal with negative 1 over Km. So it's really annoying to kind of like deal with. So you're working with double negatives and reciprocals. So we're actually just not going to cover that. I should have just taken that out. However, technically, there's some math to explain why these are there and why they behave a little bit differently. But keep in mind, Km is a substrate concentration. Km is not a velocity. It's just saying the substrate concentration at which you have reached half of your maximum velocity. So it's a substrate concentration. But we will explore a little bit more of that down here, and especially in problem number 3. So now we're just going to quickly go through problem number 2. These are just logic exercises, basically, and these are definitely exam style questions. So we want to say for the following situations, indicate whether Km, Vmax, both parameters or neither parameter would be altered. And now what makes this problem a little bit tricky, this is already kind of like a trick question that we're throwing at you. Assume that substrate concentration is in excess. So now with all that, if we take a look at situation A right here, it says to evaluate Km and Vmax after substrate concentration has doubled. Now, if the substrate concentration is doubled, but we're already in excess, we are still in excess. So we already have flooded the enzyme with way more than enough substrate than it can handle. So what this is going to mean is that neither, and I'll try to type this in, what this is going to mean is that neither is affected. And that is because if you're already saturated, if your substrate concentration is already in excess, then your enzyme is going to be firing at its maximal rate, and it can't handle, it can't go any faster no matter how much you flood it with substrate. So because of that, it's easy to say that Vmax is not affected, and Km is also not affected because Km is just saying it's a substrate concentration at which your enzyme is running at half of its maximal rate. And what's interesting about Km values is that the only way you can really change it is to change what enzyme you are working with. For example, hexokinase, which phosphorylates the sixth carbon on a glucose, basically it's going to have its maximum rate no matter what happens, and it's going to have half of its maximal rate, which is Km, likewise. And it's saying that one molecule of whatever enzyme you're dealing with is going to reach its half efficiency at a certain substrate concentration. So for hexokinase, for example, that is always going to be the same value no matter what you do to it, no matter what system it's in, no matter what human body it's in. Hexokinase, as a chemical molecule, can only fire at a certain rate. And obviously, in this case, there are no inhibitors going on. So that's A. Neither is going to be affected right here. So now we're talking about situation B, in the presence of a non-competitive inhibitor. And remember, our non-competitive inhibitor was this situation up here. My cursor kind of disappears over there. But it's this situation up here with the red dots and the green, because the non-competitive inhibitor, it's not going to care about the substrate concentration. So if we say that the non-competitive inhibitor is present, then what's actually going to happen, and I'll type it right here, V max, that should be a subscript, but that's just a little bit too complicated to do on the fly. V max is lowered, and Km is unaffected. Okay, so I'll make that just a little bit smaller. Okay. So in the presence of a non-competitive inhibitor, Vmax is lowered and Km is unaffected. So the non-competitive inhibitor is going to, by default, remember it's going to bind to the backside over there. It's going to bind to like the backside of the enzyme, and it's going to lower your Vmax. As we saw right here, the non-competitive inhibition, it went up on the reciprocal plot from where the Vmax intercept was, which is the purple dot, as you can see down here. So it went up on the double reciprocal plot, which means the velocity got slower. And that's because this enzyme, or this non-competitive inhibitor over here in the dark green that just binds to the backside, it is going to just completely invalidate that enzyme. It's going to make it useless, basically. So your overall reaction rate, velocity that can happen in your test tube or in your body is just going to be lower because you're knocking out the enzyme that does the work. So that is why, in this case, Vmax is lowered and Km is unaffected. Once again, you're going to see this a lot because Km is a theoretical value based on ideal circumstances, no competitor or no like inhibitors present. Km is never going to be affected unless you change the enzyme you are referencing. It would have to be a completely different enzyme for that to be affected. So now we're getting into something cool. If you double the enzyme concentration, what is going to happen? So you can think about it, the enzyme is the one that does all the work. If you flood an enzyme with substrate, like make it so that there's a whole ton of substrate, then nothing is really, the enzyme is going to be, firing at its max rate, and it can't handle all the rest, so all the substrate just has to wait its turn before it gets catalyzed. And if you double the enzyme concentration, then what ends up happening is that you can handle more work. And this is finally where our V max raises. And also Km, Km is unaffected again. And once again, we know about why Km is unaffected because we're not changing the enzyme in question. But when you double the enzyme concentration, you are able to achieve more. It's like you're hiring more workers out in your field. They are enzymes. So you can achieve more work as a company and you can get more profit if you want to think of it that way. So if you double enzyme concentration, then your Vmax is going to rise. It should rise proportionally. So it would be, you should just double your Vmax. So that's all that, just some logic questions. You can basically toy around and you can change any of these values and you can say, what is going to happen? Just like a quick thought exercise, if we change part B to a competitive inhibitor, I'll write this on the side. If in the presence of a competitive inhibitor, it's just as a practice question on the side, then V max, I'll give you a second to think about it. If you have a competitive inhibitor, which is this situation up here, the pinks versus the red competing for the same active site, we did reference this earlier. Just think about what would happen. And then, so now I've given you a second. You can pause the video if you want. But Vmax, if you're in the presence of a competitive inhibitor, is unaffected. And also Km is unaffected, but we know why that is the case. But Vmax is unaffected in a competitive inhibitor. This is non-competitive here, but we're talking about if it's competitive, then Vmax is going to be unaffected because you can prove this by theoretically if you flood, pull this out so you can actually see my cursor. If you flood the enzyme with its purple active site with a whole bunch of your red enzyme, which is what you want to be there, if you make so much that the pink competitive inhibitor is so drowned out and basically overridden, then your Vmax is basically the same anyway. And that's how you derive that Vmax would be unaffected in the case of a competitive inhibitor. So that's good. I will make this a little bit smaller. Right there. So you can just kind of see it a little bit more in line with everything else. All right, so now we're going on to our last question, and I'm going to try to wrap this up. So number 3 says you wish to, let me pull out my cursor again. Okay. Number 3 says you wish to characterize a new enzyme you have isolated. You have set up a series of test tubes, each containing 0.1 micromolar of enzyme in various substrate concentrations. You measure the activity of the enzyme in each tube and plot the enzyme activity against substrate concentration. The plot is shown below. So notice we have substrate concentration on the x-axis and velocity on the y-axis. This is what these curves normally look like. We did some work with the double reciprocal plot up here, but now without the reciprocals, this is what the graph is going to look like. And you can still tell some nice things even though we're dealing with curves and they might be a little bit intimidating or whatever. But this problem is going to show why there's still useful things you can point out right here. So if we look at A, and it says, A, what is the Vmax for your enzyme with the substrate? So now when we're not in double reciprocal plots, we can trust our axes. They're not inverse. So when you go up in a normal curving graph, then you are actually going up. So the higher velocities are up at the top like they're supposed to be in normal convention, and our higher substrate concentrations are all the way out here in the positive x direction as they would under normal curves. So if we talk about this, what is the Vmax for our enzyme with this substrate? All you have to really do is say, all right, well, how high along the velocity does this go? And you can follow this curve up, and it starts to kind of level off right around here. So we have to say, all right, what does that correspond to? So what I'm going to do is say that our Vmax is really just about where this intercepts our axis. We can see that's really easy to see. Our Vmax is, where this starts to level out up here. So if we follow this over, we have to say, okay, our Vmax is 50. But what are our units? Okay, so it says micromolar per minute. This could be per second. It could be any kind of concentration per second or per minute. And where the trick comes in is, well, one of the ways they can trick you is they can give you your answer choices in different units. So we know that 50 micromolars per minute is our Vmax. So we have to pick the answer that corresponds to it. And we don't, so, well, we see 50 right here. So it's tempting to pick that. However, that's millimolars per minute. And dang it, Purich, we have to do some conversion. He will throw that at you. It's just a way to see who's really paying attention and who's not. So basically, when you take that into account, then 50 micromolars, you're in 10 to the negative 6 range for scientific notation. And if you're going into millimolars, that's 10 to the negative 3. So you want to move your decimal place over 3 spots. So if you have, so I'm drawing this with my mouse, so it's not going to be as neat right now. So if you have 50 micromolars, so yeah, this is going to be ugly handwriting because I'm not doing it with my touchscreen right now. And you have this decimal point, 50.0, pretend there's a 0 right there. You're going from micromolars is negative 6, and then millimolars is negative 3. So that means you need to move your decimal place 3 spots over. So 1, 2, 3, and we know that when we do that, you have to fill in another 0. So 0.05, that would be millimolars per minute in this case. All right, and you just have to be careful. He might give you seconds on the exam. He might give you minutes on the exam. In this case, all of our units are in minutes for right here, so we can keep our observation of minutes right here. If you had to convert from minutes to seconds, you know, there's 60 seconds in a minute, so you can do just slight dimensional analysis for that. But as we can see, the answer is 0.05 millimolars per minute, and that's going to be answer choice number 4 right here. So that is our answer right there. So now let's move on to B, and it says, what is the Km of the enzyme for this substrate? And remember that, and I want you to listen to this carefully, Km is a substrate concentration. It is not a rate. Km is the substrate concentration at which your enzyme has reached half of its Vmax. And we know this, and this is written directly in the lecture side, so you can go back to that. If Km equals our substrate concentration, then Purich said that the velocity is at half of its maximal value. So what this means, you have to find the substrate concentration at which you are at Vmax divided by 2, or half Vmax. So we established up here that our Vmax is 50. So now we have to find the substrate concentration at which Vmax is half of 50, which is 25. So what we're going to do is we're going to take some less thick pen. So we need to have 25, and we have to say, all right, what is our substrate concentration where our Vmax, or where our velocity is 25? So what you do is you take 25, you go to the curve, and then you just drop it straight down. And it's not exactly on 2. My lines were just crooked, but it falls just short of 2. I hope you can see. Because 2 is technically out here, and it would be a little bit up more. But 25 is right here, so you find half of Vmax, because Vmax is 50, and now we know that Km has to be 25, or, well, half of Vmax is 25, and Km is the substrate concentration at which you reach this value. So what you're going to do is you're going to pick the closest number of the answer choices to this. So that's somewhere between 1 and 2. So we're probably looking at around something like 1.5. And we see that there's 2 1.5s. So you have to be really careful right here and pick the correct unit. And we know that our concentration in this case is in millimolars. So 1.5 millimolars is going to be our answer right there. So that is going to be our answer, 1.5 millimolars. That wasn't too bad. We just saw where it plateaued for Vmax, and then half of Vmax is 25, because that was 50 up there. And then you just find where on the on the substrate concentration axis does this line up to. In this case, it was 1.5 millimolars. So now, we did all that without calculations. I know he's throwing a whole bunch of calculations on the lecture slides, but we did it without even busting out a calculator. However, for part C, we are going to have to use a calculator, but do not fret, it is not too hard. We have to do part C, and it says, what is the Kcat for your enzyme? And let's just quickly talk about what Kcat is. Kcat is it's a numerical value that determines the frequency of catalysis as Dr. Purich liked to say. It's the catalytic efficiency of your enzyme. And this is going to be constant for every enzyme that you get. It's saying like, okay, one enzyme of hexokinase, for example, that's the example I'm going to kind of keep on coming back to. One molecule of hexokinase, no matter what beaker it's in, no matter what test tube it's in, when it's functioning at its best, it is going to have a certain efficiency. And that's what kcat is. So we have an equation for what kcat is, and this is on the slide. So I'm just going to pull up the work for the problem and like the overall equation right here. I wrote this out. The equation that you're probably going to want to memorize this, Vmax is equal to kcat, so the efficiency of your enzyme, times the total concentration of this enzyme. And you know, this varies for every single enzyme. If this is hexokinase right here, kcat is going to be different from fructose 1,6-bisphosphatase, for example. We'll learn about that one later. But basically what we're saying is that the Vmax is dependent on how efficient the enzyme is and what enzyme is it. That's what those variables basically represent. So it's literally just a 3-variable equation in this case, and you have to fill it in. So we know that our Vmax, and I'll just come back to here real quick. We know that, this is freezing a little bit. We know that our Vmax is 50 micromolars, keep that in mind. So it's 50 micromolars. And we also needed to know our total enzyme concentration. That's not in the graph, but it is in the questionnaire here. It's 0.1 micromolars. That's how much you have in your test tube or in your blood or wherever the testing site is. So 0.1 micromolars is going to be, wrong one. 0.1 micromolars is going to be our total enzyme concentration. So now you have 50 micromolars per minute equals kcat times 0.1 total enzyme concentration. You're just going to divide this term over to the other side. So you're going to have 50 micromolars per minute divided by 0.1 micromolars. And you can see how the micromolars are going to cancel out. And that's when you plug that into your calculator, you're basically timesing by 10 because you're dividing by 0.1. And you're going to get 500 1 over minutes. 500 per minute is how you would read that. Your kcat is 500 efficiency units per minute. The units are kind of arbitrary. It's just 1 over minute. That's how fast your, so in 1 minute, it's basically saying that you're going to process 500 cycles of an enzyme catalysis. So literally that's all you had to do to figure out, and here we go with the freezing again. It does that sometimes. That's all you have to do to figure out part C, which is really nice. And now finally, if we, so this would just be 500 minutes to the -1. And when you have, they will throw some scientific notation at you. 500 is 5 times 10 to the 2. I'm sure we all know how scientific notation works. And it's over minutes, minutes to the -1. So in this case, I'll just highlight this one. In this case, this is going to be our answer right there. Answer choice number 3. Okay, and finally, this is really easy. Why does the enzyme eventually plateau in our graph? Why does this happen? Now it's just saying, okay, we see math that it is an asymptote up there, but why is that happening? And if we just go over all the choices, choice 1 says the enzyme becomes inhibited at a higher substrate concentration. That's impossible because we don't have any inhibitors. You can read the problem again. There are no inhibitors in our test tubes, so it's not answer choice 1. Answer choice 2 says the enzyme affinity for substrate changes, and that's not right. As we even saw in this equation, a certain enzyme is going to have its efficiency no matter what. It depends on the enzyme total, and that will determine its Vmax. The affinity for a substrate is never going to change. There can be inhibitors that knock out an enzyme and basically make it ineffective, but it still theoretically has the same affinity for the substrate. Just the inhibitors are going to screw everything up. It's like hitting you in the head with the dodgeball or something. It's going to mess you up for a little bit. That was a really random example. Anyway, answer choice 3 says the enzyme is being degraded by proteases, and that is definitely not the case because you can read it again, there are no proteases in our containers, in our test tubes anywhere. So it's not number 3. Number 4, the active site is saturated with substrate. And this is the one that should be, the bells should be going off in your head. We've referenced this in all of the practice problems. But when you saturate your enzyme with a lot of substrate, which we can even scroll all the way back up here to this example, the red, remember this, that's the substrate you want. If you saturate it, then it's going to give your enzyme way more than it can handle, and it's going to be firing at its maximum rate. So in this case, answer choice 4 is correct. And 5 saying the substrate is being degraded, that would mean there would have to be a protease in there. And as we saw that there are no proteases in there, you can read the problem again, so there's no way it can be being degraded. Well, proteases degrade the enzyme, but you know what I mean. The substrate being degraded by something else, like a bacteria eating away at it, it's not present in our test tube. So we are all done. It's looking like this was another kind of long-ish recording, but once again, you can put it on, well, I mean, you won't hear this at the end of the video, but you can speed it up however you like. So that is the last little part of it. If this was done in class, I would have went over a little bit faster, but we're at home and you can speed this up, and I have no time limit this time, so I like to go really in depth into things and draw some pictures. But yeah, we are all done, and that's some really good enzyme kinetic practice. And knowing the logic behind a lot of it is great, and I still do acknowledge, or I still do recommend for you to try out some of the derivations, because when you're going through the derivations, they're not as hard as they seem, because Purity just throws a wall of math at you and it's intimidating. But if you go through them and you follow each derivation one by one, that's how I got this understanding of them myself. So give that a try at least once during your study. But if that still doesn't make sense, then we can just focus on all this stuff that we went over, talking about the logic behind it and kind of how to match that up with a double reciprocal plot and a normal plot like we have down here. All right, that'll be it, everybody. Have a good rest of the night. And if you have any questions, feel free to let me know.